Experimental techniques, this first one is an introduction to the lab itself. The first thing you should do when you enter any lab is to decide how you will leave it in the case of any sort of an emergency. All these labs have at least 2 exits, and it's possible to get around both ends of nearly all the benches. So the occurrence of a fire or the release of any sort of noxious gases should not prevent you from leaving the lab rapidly. At the exits are safety showers, fire blankets, eye wash fountains, fire extinguishers. Most of these items have never been needed, but you should be aware of their location and their use. Almost all fires occur in flasks or beakers, and they may be extinguished easily by covering them with a towel or a watch glass. If necessary, a fire extinguisher may be used, but by a demonstrator. The eye wash fountains are not likely to be needed, as glasses are required to be worn in this lab, either your own or some sort of safety glasses from the bookstore. Because this is an extremely messy lab at times, lab coats are highly recommended, and shoes should cover the whole foot. Hair of longer than shoulder length should be held back in some way. Hair is extremely flammable. We have an excellent safety record in this course, but only because precaution is stressed all the time. The commonest accidents are cuts and burns, almost always from glass. Broken glass is extremely sharp, and hot glass holds its heat for a surprisingly long time. Minor repairs may be carried out at C327, the storeroom for these labs. Burn jelly and small bandages are available there. Anything beyond a minor accident must be reported to the instructor in the lab. Another accident hazard is posed by the steam outlet. It is above your working surface and it's labeled. The orange handle controls the steam, and there should always be a hose attached to the outlet before the steam is released. The steam is above 100 degrees and it can scald you. You will use the steam to heat low-boiling flammable solvents. You should never expose such liquids to an open flame. Although many organic vapors and liquids are flammable, all are heavier than air. This is the reason why you are separated from your neighbor by sinks and by a trough. These help to prevent the spread of a vapor from one working surface to another where there's a flame. When you work at your bench or the sinks, you should be sure you do not put solid waste, particularly filter paper or other bits of paper, into the sinks or the troughs. Generally, there's water running, and we can have a flood very rapidly. Remember that all the solids go into waste bins at the end of each bench. We will put out recovery bottles for most of the organic wastes when these are needed. If it's necessary to dispose of noxious liquids, this should be done in the sink in one of the hoods, and it should be washed down with lots of water. You will have signed out for a kit of apparatus, and you are responsible for it. Only you and the storeroom personnel have access to your locker. Any replacements and any extra items needed, new towels, sample bottles, and so on, should be obtained from the hatch of the storeroom. The chemicals are found in several locations. The dilute acids and bases are on the bench above your working surface. Most solids to be weighed out are on shelves by the balances. The liquids are on the shelves by the blackboard unless they have unpleasant or noxious vapors. These liquids are located in a hood along with the strong acids and concentrated ammonia, and they should be handled there. Many chemicals are sensitive to moisture, so you should be sure to replace the stopper or cap on all the bottles as soon as you've finished using them. If a bottle is empty, take it to the stores and get it filled. There's a handbook placed by the blackboard for finding melting points, boiling points, densities, formula weights, and so on. All of these items should be used where they're located and not taken to your bench. There are ring stands, 2 per student, to be found beneath the blackboard. And the rings, clamps, bosses, supports for steam baths are all located in the locker below the small sinks at your working bench. All these items should be returned to their places after you've used them. There are corks and cork borers by the blackboard. There are photographs of apparatus setups on the notice boards and large photographs at one end of each of the labs. These are in addition to the photos and drawings in your lab outline itself. All of them are intended to demonstrate the customary or best arrangement of apparatus. And note that only 2 stands are needed for any setup. A great many organic liquids are immiscible with water. For this reason, you should have your apparatus totally dry for many experiments. This can be done by refraining from washing out apparatus with water unless it's absolutely necessary. Glassware may be dried by placing it in a drying oven. There's one at the end bench of each of the labs. Or you can rinse the glass with a small amount of acetone, shake out the excess liquid, and draw air through it using the aspirator or water pump that jets down into the trough between you and your neighbor. In the distillation experiments you're about to do, you can simply shake out the excess liquid from the pieces of apparatus and use it again. There's often no need to use water at all. You will record your lab results and answer the questions on the report sheets that are supplied to you. Avoid using scraps of paper and enter your observations directly into the record. A list of dates on which sets of completed experiments are due will be given to you. Most of this information and a good deal more is found in the introduction to your lab outline. You should read through this material several times during the term. The second half of the lab outline and the answer sheets will be provided at the start of the second term. The first experiments which you do in this course are concerned with distillation, and this involves setting up apparatus and carrying out relatively simple distillations of a single pure liquid and then of a mixture of 2 pure liquids which you will attempt to separate, first by simple distillation and then later on by fractional distillation. Now I've set up part of the equipment to save some time, and then we'll go through the procedure of arranging the rest of it and getting it ready, carrying out the simple distillation. You have apparatus that has ground joints, standard taper joints, which take a small amount of the lubricant which is contained in your kit. You put a little at the top of the joint and then rotate it in the cone in the socket to provide a smooth seal. Each one is treated in the same way, and then the joints are slowly moved together. The thermometer adapter is greased for the standard taper joint, but the thermometer is lubricated with a different lubricant. A small amount of glycerol is placed on the thermometer and this is then rotated, and it provides a smooth fit for the thermometer. Then the adapter is put onto the top of the distillation head and again rotated to provide a smooth seal. The height of the thermometer is adjusted so that the bulb of the thermometer will be bathed in vapor as the distillation takes place. You can see then if it's at this height, the vapor will go up and across into the side arm, bathing the bulb of the thermometer completely in the vapor and giving you the true temperature of the distilling liquid. We want to put about 25 milliliters of the carbon tetrachloride into the distillation flask, which is a 50 ml flask. This is about the normal amount of material you put into a flask roughly half the volume of the flask. If you put too much in, then in the process of boiling, some of it may be carried over mechanically into the receiver, or if you use too little liquid in the flask, too much of it is lost, simply filling up the flask with vapor. We then take a couple of boiling stones or boil easers, which provide a steady stream of bubbles when they're heated, and this prevents the pure liquid from bumping. One or two is all you need, but you should use a fresh one each time you start a distillation. The distillation head is placed into position, and the condenser is adjusted so that it too makes a smooth seal. Now this joint at the top of the condenser, this one is the most crucial joint in the apparatus because it's here that the joints come apart most often, and here that vapor can then escape from the system. At the other end of the condenser, we put on a distillation adapter, again lubricating the joint with a small amount of the lubricant, rotating the joints together until there's a smooth seal. And now this small rubber leash can be used to hold the distillation adapter in position, prevent it from slipping off. The amount of liquid that you're distilling can be measured by placing one of the graduated cylinders in position as a receiver and adjusting it so that the drops will fall into it. Then it's necessary to start up the water in the condenser. This fills the condenser then from bottom to top, where it flows out again and down into the drain. Making sure that the joint here in particular is still tight, that all the joints are smoothly lubricated, that the thermometer is in a position where you can read it. Then we light up the Bunsen burner. Adjusting the burner so that we have quite a small flame and not too hot a one. Remember that the boiling point of carbon tetrachloride that you use first is quite low, about 75 degrees, so you want quite a small flame. Then, placing it in position, we can raise the burner chimney to keep the flame from blowing around. It will very soon heat up to boiling, and we will have probably to adjust the flame several times in order to make sure that it isn't distilling too rapidly. Now you can see that the liquid is starting to come to a boil, and soon the vapors will start to rise up into the distillation adapter, flow over into the side arm, and with the cool water condense and drop down into the receiver where we measure the amount of water, of the distilled liquid. Now it's boiling quite rapidly, so again we cool down the flame slightly by cutting off the amount of air, cutting down the amount of gas flowing, moving the burner off slightly to one side so that as it distills, the drops are coming out at a rate which you can see. Separate drops falling from the end of the receiver, of the distillation adapter into the receiver. And you read the volume and follow the temperature at the same time. Now you want the drop rate flowing at such a rate that you can count the drops 1, 2, 3, 4. This is going somewhat too rapidly, and it's necessary to cut the flame back slightly or move the flame off to one side so it isn't distilling too rapidly. After the distillation has been completed, you will want to carry out a fractional distillation, and this involves modifying this simple distillation apparatus to include a distillation column. This is a simple condenser which has been packed with a small amount of curly steel sponge, which acts as a heat exchanger and a distillation column packing. I have assembled the apparatus for fractional distillation. You'll notice that the principal change is that the fractionating column is now in position between the distillation flask and the distilling adapter. The stainless steel sponge in between provides a means of condensing the heavier liquid as the vapors rise up, allowing the lower boiling liquid to flow out and distill over into the receiver. Now, it's not a very long or a very efficient fractionating column that you have, so the separation is not very good. But it does illustrate the principle of fractionating, and you will carry out a distillation which will provide a small amount of separation. The mixture of carbon tetrachloride and toluene has fresh boiling stone in it. The apparatus has been assembled and the joints have all been lubricated, especially this joint at the connection between the distillation head and the condenser. A graduated cylinder again is used as a receiver, perhaps the small one for fraction A, perhaps the larger one for the intermediate fraction. The Bunsen burner is lighted again, and this time a little larger flame than the simple distillation. Again, the burner chimney is adjusted to prevent the drafts from blowing the flame around. Now, when it comes to the boil, the mixture of the two vapors will pass up the distillation column. They will start to lose their heat to the stainless steel sponge and condense and flow back down the column. As usual, it's distilling much too rapidly. I have to cut my flame back quite a lot. Small, luminous flame, and the vapors pass slowly up the column, heating the steel sponge. The vapor line is now up to here. It's slowly rising up, and eventually it will reach the thermometer bulb and bathe the thermometer bulb in the vapor of more of the lower boiling liquid and less of the higher boiling liquid. There will be a certain amount of separation taking place on the column. Now the liquid is again distilling quite rapidly. Move the flame over to one side slightly, and the condensed vapor starts to flow out into the receiver, and again we want it flowing at such a rate where we can see separate drops falling into the receiver. And then we will continue until the temperature starts to rise above the boiling point range for your collection of fraction A, then switch receivers and collect the intermediate fraction, and finally the fraction B. Then the intermediate fraction is distilled fractionally once again through this column. This enables you to achieve a moderate separation of the two liquids, carbon tetrachloride and toluene. The Bunsen burner, which is on your working surface, is quite a versatile piece of equipment, and you should learn how to use it to maximum advantage. On the base of the burner, there's a valve that controls the amount of gas that's admitted, and as well, you can rotate the barrel of the Bunsen burner to admit more or less air into the mixture of gases. You have, as well, a burner chimney or flame guard, which is usually on the barrel of the burner most of the time that you're working with it. It can be raised to prevent the wind from the open windows or people walking by from blowing your flame around. In lighting the Bunsen burner, there are quite a number of different ways you can do it. A useful way is to close off all the gas completely at the base of the burner. Then you open the gas tap quite wide to give yourself lots of gas pressure. And open the valve at the base and allow a moment or so for the air to flow out of the system, and then the burner should light quite easily. Now, the flame I have here is an almost colorless flame with only a small blue cone in the center of it, and this is a very hot flame. The blue cone represents the burning carbon monoxide. If we close off the air from the flame, then it becomes increasingly luminous, smoky, much cooler flame. We can adjust the amount of gas to give us a quite small flame, and then the amount of air to give it a little warmer flame, so that one about this height is quite useful for most of the distillations which you carry out in the lab. Then you adjust the height of the burner chimney to prevent breezes from blowing the flame around. When you want to turn off the flame, you can do so at the base of the burner. Then you have, in addition, a fishtail, wingtop, flame spreader, which fits over the barrel of the burner and is useful for bending glass tubing. There are a number of sizes of burners and of flame spreaders, and you should choose one that fits snugly on the barrel of the Bunsen burner. Then, opening the gas again, we can light the burner and then adjust the amount of air to give us this broad, quite hot flame that's useful for bending glass. When you've completely finished with the use of the Bunsen burner, you can turn it off either at the base or at the tap. But at the end of the afternoon, you should always turn off the burner at the tap itself to make sure there's no gas left flowing in the burner system. The melting point of an organic substance is one of the best indications of the purity of the material. The samples from the bottles in the shelves in the lab and the samples you recrystallize during this course will have melting point ranges from around 2 to 3 degrees. A really specially purified material might have a melting point of 1 degree or even less, but seldom in using a capillary do you find a melting point range that's less than a degree or so. This is because mercury is a liquid metal that conducts its heat very rapidly from the bath oil, where the solid material transmits heat fairly slowly from particle to particle, even though it's packed tightly into the capillary tube. In the melting point apparatus, we have a solid material placed in a capillary tube. The size of the sample is generally about 3 or 4 millimeters in length. Anything smaller than that makes it rather difficult to see the melting taking place, and if you have too much of the material, then you lose a lot of the accuracy of the experiment. The bath oil is heated with a flame at the bottom left-hand corner, as I've set it up here, so that the hot oil will rise and stir the bath oil by convection. The temperature rises, and you observe first the appearance of a small amount of melted material, the beginning of the melting point range. And then finally, when all of the solid disappears into the melt, that's the end of the melting point range. You can heat the bath fairly rapidly until the temperature rises to perhaps 15 or 20 degrees below the melting point of the compound, and you can always check with a handbook to make sure of the melting point you should expect. Then slow the heating down so that the temperature rises very, very slowly indeed in the vicinity of the melting point. Remember that the mercury will transmit the temperature change very much more rapidly than the solid material. The usual mistake of students is to heat the bath too rapidly and obtain too wide a melting point range, because the mercury thread will have risen very rapidly while the heat is transmitted fairly slowly through the solid. This material is now approaching its melting point, and I've slowed the heating rate down quite considerably, and you should soon be able to see the melting start to occur. The material will soften and start to show a small amount of liquid. The amount of liquid will increase until all of the solid material will disappear. We're now well into the melting point range of the material. The amount of solid is slowly decreasing as the liquid increases. And finally, the last of the solid disappears, and that constitutes the melting point range of the material, which in this case was a little less than 2 degrees. The presence of an impurity in a pure organic compound invariably lowers the melting point and increases the melting point range. If you make deliberate mixtures, as you do in the melting point experiment, then you will find quite a variety of ranges and melting points for the mixtures of urea and cinnamic acid, as indicated in the diagram you'll find in your lab outline. There are also mixtures of compounds that may melt above the melting point of the two components. However, in this experiment, we'll look at the melting point of a mixture of two compounds to see that the melting point range is greatly increased. Once again, you need to heat the compound quite slowly in the region of the melting point. And you see that even now there is slight indication of something happening. And we're now about 20 degrees below the melting point of each of the two components. We now have a melting point range of nearly 6 degrees. Now the melting point range is just about 8 degrees. You see how unevenly the sample is melting, even though it was a fairly finely ground mixture of two compounds. Now the range is close to is just over 9 degrees. Now the range is 10 degrees. Range is just over 12 degrees, and it's still not completely melted. Now we seem to be just about at the end of the melting range. It's over 13 degrees. Still, the last traces of solid have not completely vanished. Now I think the melting is complete, and the range is just over 14 degrees. So we get an enormously increased melting range for a random mixture of two solid compounds whose melting points are not very greatly different from one another. In this experiment, you're going to recrystallize some impure acetanilide, which has been deliberately made impure through the addition of both materials that are more soluble and less soluble than acetanilide in the water that you're going to use to recrystallize it from. You put your weighed sample into an Erlenmeyer flask, and then, in order to save time, you'll have heated some water on a flame to near the boiling point. You can add the nearly boiling water to the amount of about 100 milliliters for the 5 grams that you're going to recrystallize. And then bring the liquid back up to the boiling point. You want to dissolve the substance in a minimum amount of water right at the boiling point. Now, while the material is dissolving, you should be warming up a short-stemmed funnel on your steam bath. Place it upside down on the steam bath and let the steam run slowly so that the funnel is preheated. At the same time, you want to prepare a fluted filter paper from number 4 filter paper, 11 centimeters size. If the material is now dissolved, you can stop heating it for a short time and get the filter paper prepared. This is done by folding the filter paper first in half, then in quarter, then open it and Again, fold each quarter in half in the same direction. Now you have 4 sections, and each section is then folded back on itself in the other direction, so that you get an alternating or zigzag pattern of folds. Make sure it's creased, and then when you open the filter paper completely, you have a fluted paper that will sit in your funnel but have only a single surface all the way around for rapid filtration. Now the funnel is heated, the sample back up to the boiling point, and carefully check to make sure that the oily material, the oily droplets, have all gone into solution, but there will be some solid material, sawdust, which doesn't actually dissolve. Then you carefully remove the funnel and place it into the flask, which you're going to carry out the filtration. Put the fluted filter paper ready. Then lift out a ring or 2 and place flask and funnel in the steam bath, and add back the rings to maintain the heat around your receiver flask. You can also put a small piece of folded paper between the funnel and the flask to make sure that the vapors are able to escape from the flask. Now, as you boil the liquid, you continually lose your solvent, so you'll probably need to add some more solvent from time to time. But bringing it back up to the boiling point, we can now carry out our filtration, gravity filtration using fluted filter paper, preheated funnel, into a flask that's kept warm. This prevents the crystals from separating from the hot liquid during the course of the filtration and blocking the funnel or the filter paper. So we will then pour the hot liquid into the fluted filter paper, and it filters through quite rapidly through the number 4 filter paper. Carry out the complete filtration. Use a stirring rod to direct the flow of the liquid into the fluted filter paper. May be necessary to bring it back up to the boil again from time to time, and if oily liquid appears to be separating, you may need to add a little more of the warm solvent and keep it near the boiling point all the time. At the end of the filtration, there may be solid material left in the fluted filter paper. If that's so, then bring a small amount of extra water to the boil and pour it through to dissolve the last of the crystals. When the filtration has been completed, can remove the funnel and then remove the flask from the hot steam bath. Now we have a clear solution of our acetanilide in very hot water, and we allow it to cool slowly so that the crystals will form and grow quite large. If we chill it very rapidly, we get very small crystals, which are both difficult to filter and tend to absorb onto their surfaces the more soluble impurities. So we'll allow this now to sit quietly and grow large crystals. Now that the crystals have had an opportunity to grow and have been chilled down, first in cold water and later in ice, to make sure that all of the crystals have come out of solution, we can prepare to remove the crystals from the mother liquor, that is the solvent, by suction filtration. We use a suction flask with a Buchner funnel on top and a filter vac to seal in between. The Buchner funnel has a plate which is perforated, and it takes a number 5 hardened filter paper, much more retentive and slow than the one you used for gravity filtration. It should cover the holes of the plate of the Buchner funnel, but not overlap up the wall. First, you'll wet the filter paper slightly in order to permit it to seal over the holes of the Buchner funnel. Then, placing it on the filter vac, turn on the water pump. The pump is turned on full. Then, press the Buchner funnel down somewhat to seal it firmly onto the filter vac onto the filter flask. Then, the solvent is slowly poured into the center of the Buchner plate. You can see that the solvent is rapidly drawn through and the crystals are left behind on the plate. And so you continue to add your mixture. Generally, you tend to pour the solvent off first, and then towards the end, give it a swirl around and transfer most of the solid material and the rest of the solvent onto the filter plate. To remove the last of the crystals, you can use a glass rod with a rubber policeman on it to wipe down the walls, and then add a small amount of ice-cold water or the solvent that you're using to recrystallize, swirl it around, and transfer that onto the plate. The main thing is not to add too much more solvent and to make sure that the solvent you do add is quite cold. Once the crystals have been sucked down onto the plate firmly, and most of the mother liquor is now drawn through, you want to wash the crystals with solvent to remove the last of the mother liquor from the crystals. So first, you break the vacuum. Then, pour a small amount of the ice-cold solvent onto the crystals. Swirl it around slightly, make sure that the crystals are washed by it, and then restore the vacuum and suck off this solvent. This is done 2 or 3 times, making sure you use only a small amount of solvent each time and that it is ice-cold solvent, and trying to be sure to wash all of the crystals thoroughly when you do so. Once the washing has been completed, You can allow the suction to continue for 5 or 10 minutes so that air is drawn through the crystals. This helps to dry them out, especially if the solvent is one like alcohol, which will evaporate fairly rapidly. Once all the solvent has been drawn through and the crystals are fairly dry, then you break the vacuum once again, and with a spatula you can remove all the crystals onto a watch glass or onto a filter paper and allow them to dry. Some of the crystals you prepare will sublime into the air fairly rapidly, and they must be put into a sample bottle and sealed up immediately. Others with high melting points will dry in the open air over a period between two labs. This then is the procedure of recrystallization for the purification of a solid. This is the separatory or dropping funnel which you have in your kit, and in this course you'll use it principally for two purposes: to enable you to separate two immiscible liquids, and also to add slowly, drop by drop, a reagent to a reaction in progress. We'll look at its use as a separatory funnel for washing and separating two immiscible liquids first. There is a stopcock at the bottom which may have a glass plug or possibly a Teflon plug. The glass plug needs to be lubricated. The Teflon plug doesn't necessarily need to be lubricated. For lubrication, you use the ordinary Lubriseal from your kit, and you put a small amount of the lubricant at each end of the ground surface, not in the middle, because there's a small aperture which enables you to separate the lower layer. You then put the plug back into the barrel of the stopcock and rotate it slowly until there's a nice smooth seal, holding it firmly in place. Then put the retaining rubber ring or metal ring back on the other end of the stopcock and make sure it's closed. We'll put some water into the separatory funnel to represent an aqueous layer of some sort. It will contain the more polar materials. Then we'll put some carbon tetrachloride into the separatory funnel to represent an organic layer, and it will contain mostly covalent materials. Then you put the stopper in the top. It doesn't have to be lubricated. Put it in firmly, then hold the funnel either with one or two fingers, or make sure that the stopper is held well in place. Then rock the funnel back and forth to mix the layers thoroughly. You should vent through the stopcock every few minutes to make sure that no pressure builds up in the funnel. Low boiling liquids become warmed by the heat of your hand, build up a pressure, or you may be carrying out an actual separation where there's a reaction involved and some heat is generated. So vent the separatory funnel from time to time. Then remove the stopcock and place the separatory funnel in a metal ring. Because these are two pure liquids, the two layers separate almost immediately. In practice, you may find that they don't separate cleanly, and by gently swirling the separatory funnel, it's quite often possible to sharpen up the interface. Then we remove the lower layer using the stopcock, dropping it down into a flask or beaker to the receiver. You follow the interface as it drops until it just reaches the top of the stopcock, and then you close it. Having removed the lower layer through the stopcock, we remove the top layer from the top of the separatory funnel. You'll remember that there's a small aperture in the stopcock. This is now filled with the lower layer, and to draw the upper layer through it now would contaminate it. So the lower layer goes through the bottom, then the upper layer is poured out the top. In the experiment on extraction, you'll be removing the material from the water layer into the carbon tetrachloride layer, or vice versa. In this experiment, we had carbon tetrachloride and water. Carbon tetrachloride is denser than water. It's on the bottom. In other experiments, the organic layer may be on the top. You should never throw away either layer until you're absolutely sure which one is which. You can always check a water layer by simply adding more water to it and seeing that there isn't or is a second layer formed. Later on in the course, you'll use this as a dropping funnel to add reagent to a reaction in progress. This is the apparatus set up for steam distillation. You'll use it 2 or 3 times during the course of Chemistry 240. I've saved some time by completely assembling it. The important features that are different involve the use of the steam trap with a cork, which you'll have bored with 2 holes in it, 2 bent glass tubes, one going in, one going out, connected through rubber tubing, or this can be all one continuous piece of glass tubing, bent again and down right to the bottom of the steam distillation pot. The steam distillation is started by turning on the condenser water first, and then making sure that the rubber tubing with its small screw clamp permits the extra water to run down into the sink or into a trough. You turn on the steam first, but before you do that, you should probably check to make sure that most of the condensed water is out of the system. If you disconnect this tube and flush the extra water down the drain, then reconnect. Make sure the cork is seated tight in the bent adapter. Make sure all your joints are well sealed, particularly these up here where a certain amount of strain can develop in the apparatus and pull the joints apart. And then turn on the steam so that there's a moderate current of steam flowing into the steam trap. Again, there's quite a lot of water and it will run down the drain. Now you control the amount of steam that's going into your steam distillation system through the use of this small screw clamp. As you tighten it up, it will cause more and more of the steam to flow over and into the steam distillation pot. And you can see now in the steam distillation pot that it's starting to churn and the liquid is heated up with the steam, and eventually when the 2 liquids have a vapor pressure whose sum is 760 millimeters, or atmospheric pressure, they will steam distill together. Now, It may be necessary from time to time to adjust the screw clamp so that more or less steam flows into the system. And you can do this then also permitting any extra water that builds up in the steam trap to flow down into the drain by opening the screw clamp briefly and then closing it again. But as soon as the temperature of the combined liquid starts to build up, you'll start to see vapor rising up and through the Y tube here. This is placed in the system to prevent any splash from splashing directly over and into the receiver. Now you can see that there are mixed vapors starting to recondense and flow back down, and the hot vapor mixture is slowly heating up this section of the tube, and the vapors are rising and eventually will pass over into the side arm and be condensed in the condenser and flow down into the receiver as drops of liquid. Since benzene is distilling over first, it will come quite rapidly. You can see now that there is some benzene flowing down into the receiver. When most of the benzene has been steam distilled and the bromobenzene starts to come, then the rate will probably slow down, and you may have to adjust and increase the rate of steam flow. And this will continue until all of the benzene, most of the bromobenzene, have steam distilled. And at that point, some of the para-dibromobenzene will start to steam distill as well, and because the condenser is cold and the para-dibromobenzene is a solid at room temperature, you'll start to see a buildup of white material here. But this will not take place until quite a large amount of material has steam distilled. We've now reached the point where there's a substantial amount of solid material starting to condense out at the bottom of the condenser, at the coldest part where the incoming water is hitting the side of the condenser, and it's stretching all the way up to about here. At this point then we can change the receivers. Probably a smaller one will do for the para-dibromobenzene. And once this has been done, we turn off the water in the condenser and disconnect it briefly, allow it to drain. In this way, the steam running through the system will soon warm up the inside of the condenser and permit the solid material to melt. As soon as the steam warms this up, it will start to melt and flow down into our receiver. You can see it's now starting to disappear. As soon as that takes place, we can start the condenser flowing again. In this way, the solid material will start to condense again, and it may be necessary to stop the condenser water, perhaps even drain the condenser again. But the solid material, the para-dibromobenzene, is carried down into our receiver. And depending upon the temperature in the receiver, it may or may not crystallize there. Now, in our steam distillation pot, we have now almost entirely water. There is only a very small amount of the second layer, which will be para-dibromobenzene in the bottom of the pot, and it will soon steam distill. And you can tell the that the reaction or the steam distillation is almost over. The liquid is no longer a mixture of two layers, but is now almost entirely water going over. And you can see in the condenser there's hardly any white material built up anymore, so the steam distillation is essentially over. Again, one can stop the condenser running and allow the last of this to melt and run down into the receiver, but there's practically nothing left in the distillation pot to steam distill over, and the steam distillation is complete. So we can close it down first by opening the valve, the screw clamp, on the tube running down into the drain, and then turning off the steam, disconnecting the cork, and removing the distillation tube. And the steam distillation then is complete.